Welcome. My name is Chris Wills, and I am Director of Training for RDI Technologies. And this is a basic vibration analysis overview. And the reason we're making this video is specifically for students who plan to come to the basic motion amplification training. And maybe you're worried a little bit because we'll be talking about vibration analysis and doing some vibration analysis in the class, and maybe you don't have any experience with vibration analysis. So we'd like you to review this video just so that when you come to the class, you'll have maybe a better understanding of some of the terms we'll be using in the class. One of the topics that will come up quite often in the basic motion amplification training is vibration analysis, because one of the major benefits of motion amplification is the ability to perform vibration analysis without having to touch or make contact with the equipment being analyzed. That's not to say that anyone who uses motion amplification needs to be a vibration analyst. On the contrary, motion amplification is very often used to identify problems or evaluate equipment and assets without the need for traditional vibration analysis. But because our system includes the ability to perform non-contact vibration analysis, we will be spending some time in the basic motion amplification training describing how to acquire and display vibration data. And if you don't happen to be a vibration analyst, it may be helpful to have a basic understanding of the terms we will be using in the class as we discuss vibration analysis. The first term I'd like to define is simply the word vibration, which means movement of a body about its reference. So when we look at a spectrum, a vibration spectrum, which of course is a display of amplitude versus frequency, we see two scales. We see a vertical scale on the left-hand side, which is our amplitude, and we see a horizontal scale on the bottom, which is our frequency. Now, the amplitude is what we consider to be the amount, or very often the severity of the vibration. And notice that in the left-hand side where we have that amplitude scale here, that the values, it says peak to peak displacement in mils. 1 mil is a unit of distance. It's 1/1000th of an inch. Or in the metric scale, we would use microns, where there are approximately 25 microns in 1 mil. This measurement is what we call displacement, which by definition is a measurement or an expression of distance measured peak to peak. So to describe what peak to peak is, let's just say that we've got this asset here, this body, and without any vibration or without anything being applied to it, it just sits in one position. Now, when we apply a force, let's say a rotational force of the shaft that maybe has a little bit of imbalance or some misalignment, it moves from its resting position. So in the horizontal scale, it would move both to the left and to the right with its resting position as a reference right in the middle. And so if it moves, let's say to the left, 1/2 mil, and then it comes back to its resting position and moves to the opposite direction, 1/2 mil, well, the measurement we would get then in displacement would be 1 mil, 1 mil peak to peak. So notice now when we look at our spectrum, the size of the peak scales to the amplitude scale at about 1 mil of displacement. Another way we can both measure and express a vibration amplitude is to use velocity. So velocity is a measurement or an expression of distance per unit of time, or maybe in plainer language, speed. And so kind of like speed, where we're used to measuring speed maybe in miles per hour, in the vibration world, velocity is measured and expressed in inches per second, or in the metric system, millimeters per second. And so now, if we view this spectrum, note that the amplitude scale is no longer in displacement in mils, it is now in velocity in inches per second. And here our peak scales to about 0.12 inches per second of velocity. And then a third way we could measure and express the vibration amplitude would be to use acceleration, which is the measurement and expression of change of velocity per unit of time. And the standard unit we use to measure and express acceleration is Gs, where 1 G would equal approximately 386 inches per second, or you might say inches per second squared. And so if we look at our spectrum now and we're looking at Gs, note that the amplitude scale is RMS acceleration in Gs, and the scaling of our peak is about 0.06 Gs. So we might say, yeah, we have about 0.06 Gs of vibration. And so there are three different ways we can both measure and express vibration amplitude: displacement in mils or microns, velocity in inches per second or millimeters per second, and acceleration in Gs. And often it's just a preference of the vibration analyst, whether he or she uses displacement, velocity, or acceleration. And another thing to know about these amplitude units is that they're all mathematically related to each other. So you could measure the displacement and then mathematically calculate the velocity, or you can measure the velocity and mathematically calculate the acceleration. Remember that for motion amplification, we are measuring the displacement, but we can mathematically calculate the velocity or the acceleration from the displacement measurements. Next, I'd like to talk about the frequency of the vibration. And the term frequency means the interval which something occurs per unit of time. And another term that I'm going to use right now is the term periodic. Most of the time when we're analyzing things in our vibration spectrum, we are looking at periodic vibration, which basically means the motion or the vibration happens in a pattern. It recurs at a regular interval, rather than the opposite of periodic would be transient, where transient would be more of a random type of motion or vibration. So looking at the frequency scale of the spectrum now, which is the horizontal axis at the bottom, the location of the peak identifies the frequency of this vibration. So note here that it says frequency in hertz, and the peak falls at about 42. So we'd say the vibration is happening at a periodic rate of about 42 hertz. Of course, the term hertz means frequency as cycles per second. And so hertz is just another way of saying cycles per second. So we could look at this and say the vibration occurs about 42 times per second. Another way to express a vibration frequency is to use CPM, which is cycles per minute. And so in CPM, when I look at the spectrum now, notice the scale has changed and the peak lines up at about 2600. So we'd say the frequency of vibration is 2600 cycles per minute, which would basically be taking the value we had in hertz and multiplying by 60, because there are 60 seconds in a minute. And then the third way to express a vibration frequency would be to use orders. Orders is the expression of frequency as cycles per rotation. So with our vibration that occurred at 2600 cycles per minute, if this machine happened to have an RPM of 2600 RPM, then we would say the vibration occurs at one order because the vibration cycles once every time the shaft makes one complete rotation. And so there are three ways to express a vibration frequency. Hertz is cycles per second, CPM is cycles per minute, and in the case of rotating equipment where the rotational frequency or the RPM is known, we could express the frequency as orders, which is cycles per rotation. And then there's one last term I'd like to define as it relates to the vibration spectrum, and that is Fmax. The Fmax is the maximum frequency displayed in the spectrum. And so when I look at this spectrum and I look across the frequency scale, the Fmax in this spectrum is 60 hertz because the data ends at 60 hertz. So if there were a vibration that were occurring at some frequency higher than 60 hertz, I would not see it because the measurement actually stops at 60 hertz. So in this example, my Fmax is 60 hertz. Another type of vibration plot is known as the waveform. And the waveform is a display of amplitude versus time. So this is a sample waveform where we still have an amplitude scale on the left-hand side, but the amplitude scale doesn't start at 0 and just run up. We've got 0 in the middle, and we've got the positive and negative values in this waveform representing motion in both directions from the resting position. And then instead of frequency on the bottom, we have time. And this is considered to be more of the raw data because it's the waveform that is used to generate the vibration spectrum. And the term we use to describe the mathematical process of converting the time waveform to the spectrum is known as FFT, or fast Fourier transform, where we start with the waveform, we get our waveform data, the software then uses all the values in the waveform to calculate the spectrum using FFT. So that's about it. There's really not a lot you need to know about vibration analysis before you attend the basic motion amplification training. We get plenty of students who have absolutely no vibration analysis experience at all, and they do just fine. Remember, this is not a vibration analysis class. This is a motion amplification class, and I think you'll find that motion amplification is a lot easier than vibration analysis. I'm looking forward to seeing you in an upcoming basic motion amplification class, and if there's anything I can do to help get you enrolled in training, please don't hesitate to contact me or our training coordinator, Trivy Kelly.